Next, we've got Josh and Teddy, and I've been looking forward to this talk for a long time, and it looks like they've got some really cool stuff to show you. So let's give these guys a big party track welcome.
All right, so my name is Josh Dadko. This is Teddy Reed. Today we're going to learn how to make a hardware implant. So basically, I'm just going to do a quick introduction here, what the NSA Playset's about, what we're trying to do. We're going to go over some I2C attack surfaces. So you don't know what that is yet, but we'll talk about that. We're going to build up a hardware implant. So we're going to start with the attack surface, get the controller module, get a little GSM going. We're going to show how we can improve this technique, some suggestions for future work, and some improvements that we've made that we think improve on the NSA technique. We're going to wrap up and then do a live demo. So what is the NSA Playset? So last year, so if you went to Mike Osmond's talk, he kind of introduced it, but last year there was a leaked Ant catalog. It had a bunch of hardware toys, and the idea is that we look through them, right? We should understand what these capabilities are so that we know how to defend against them. So there's 4 talks with this moniker. There's one on Friday, you're in track 1 now, and then right after this one, so you get a twofer, so stay for GSM sniffing, and then at 1400, you can see PCIe stuff. So yeah, so this is kind of inspired by the NSA Ant catalog, right? So they have this hardware hacking catalog where you kind of flip through it, and you're like, oh, this is interesting, what do I want to buy? How do I want to attack this target? And so one of the attacks was this device called WAGONBED. And WAGONBED didn't actually have its own slide in the Ant catalog, which leads us to believe that we don't have all the data, but it was referred to by 2 other attacks, Iron Chef and Crossbeam. And what we know about WAGONBED is that it was a I2C controller board that somehow attached to a PC. In this case, they actually spelled out a very specific version. It was an HP ProLiant server, which if you have that, I would be really interested if you looked in and saw anything, but no one has come forth. But a very specific model of an HP server. And it was some modular capability, right? So they could add a GSM module to implement Crossbeam, and then they could exfiltrate data over GSM. So you kind of look through it, and you're like, oh, this is kind of nice. But you really kind of wonder how that works. At least I did. So let's identify some of the requirements for this implant. So all we know really is that it must attach over I2C, which we'll go over that in a second. And it must have some modular component, and it has to reach back over GSM. So those are the requirements from the leaked documents, but the NSA Playset, we have kind of other requirements, right? So we want these tools to be easy to use, right? So this technique, implementing this technique should be easy and approachable. It needs to be open source hardware. So I'm a big believer in open source hardware, right? You should release the design schematics, the BOM, everything, so other people can learn from the technique and re-implement what you're doing. Also wanted the device to be flexible, right? So I didn't want some one-off hardware implant. I wanted some generic hardware implant that could be useful on multiple platforms. And lastly, it should be fun. So there are some single chip solutions that will kind of do this, but they're proprietary, they're under NDAs, so that's not fun. So we want to make it fun. And this slide here, we're going to come back to a couple times. So this is the breakdown of the implant, right? So we're going to, as we go through the presentation, we're going to update this so that we kind of know where we're at. So right now, all we know, it's over I2C. This middle platform is the hardware implant. So we know that there's some controller. We don't really know what that is yet. We know it talks to a GSM module. We don't know how it talks to it. But then that GSM capability gives you some reach back. So what is I2C? So I2C is a serial bus. It's typically found on embedded systems because it's 4 wires. You just need data and clock, and then power and ground. It's a multi-master, which basically means what it sounds. You can have multiple masters on the bus. There is some collision detecting. There's some details to the protocol. You have multiple slave devices. These are addressable, so you can write to the device. And if you guys do anything with like temperature sensors or any of that kind of stuff, right, they'll have an address that you can talk to. The standard speed, so it's not a very fast protocol. Standard speed is about 100 kilohertz. It can go up to theoretical 3.2 megabits per second, but overall, it's not really fast. It's meant for kind of EEPROMs and these kind of low embedded devices. So if you're more of a visual person, this is a visual example, right? So the top picture will kind of show this bus, right? So we have multiple masters. We have an EEPROM slave device on this bus, a sensor slave. So if you're ever doing any kind of reverse engineering of an I2C, right, you're typically looking for those 2 data lines Also look for pull-up resistors, right? So you see those pull-up resistors coming from the voltage rail. Some of the system-on-a-chip processors actually have pull-up resistors internally, so they may not be there, but that's usually a good sign. And at the bottom, you see like a logic analyzer dump. And basically, the master controls the clock. It sets the clock frequency. And then depending on the rise and fall of the data line, that basically decodes to a different value. And then that's how they communicate. So, okay, so now we know some things about I2C. Let's start thinking about how we can use I2C to attack a PC. Well, I2C, even though it's an embedded protocol, it shows up pretty commonly in different computers. One thing you'll show up is on RAM. There's an EEPROM typically, which has some settings and data about the RAM. So that could be a potential attack surface. You can certainly, attach like a SOA gate clip and get on the EEPROM, or you can kind of like solder fly wires to it. But that's not fun, right? You got to open a case, you got to do some soldering, right? So this is not fun. You could do it, but it didn't meet the fun requirement. PCI and PCIe, now this one's interesting because PCIe has a SM bus, which is basically I2C. So if you make a PCIe card, put that in, right, you can use I2C. So now you can imagine if you made some sort of like card, you can get that into a device, right, you can get onto I2C. And so what's nice about I2C from an attack point of view is that there's no like hot detect, right? It doesn't launch any drivers, you just kind of add to the bus. Unless you're actively probing for that device, you would not know, right, something's on I2C. So that could be interesting, but again, you got to open a case, you need like a screwdriver and all that stuff. So we're going to count that. Yeah. So battery controllers. So if you had a laptop, right, and it has a battery, there's an I2C battery controller. That could be a nice way to get in. But then you're only talking laptops, so that didn't really meet the whole general purpose thing. So if there was an adapter that kind of fit every PC or server that had some sort of I2C protocol. Well, what about video? So why is there I2C? So I2C is on a video adapter, but why is that, right? So have you ever wondered why when you plug in your video adapter, you can automatically detect the resolution? So that resolution is stored in an EEPROM on a monitor, right? So there's I2C coming out of every video adapter. And the way the video adapter works is basically with two different protocols. So the data inside the EEPROM fits this thing called EDID, which is extended display identification data that has the information about the resolution. And it uses DDC, which is a data display channel, but it's basically the transport is I2C. And now I'm going to turn it over to Teddy to talk more about EDID.
How's it going, everyone? Woo! All right. So think of EDC as like the next layer in the protocol stack above I2C. And there are drivers in whatever operating system you have for whatever video card you're using or whatever system, OEM, independent service vendor board that implements the video adapter, that's running in software land, supporting this protocol, parsing it as it comes out of the display adapter or whatever you're attaching to, VGA, HDMI, so on and so forth. You can query this. If you're in Linux, you probably have this application as part of your standard userland set of binaries. It will query I2C, the I2C bus, and it'll ask for this information for every display adapter that your system reports is in use. And by use, I mean attached, right? It's there. Like Josh said, there's no hot swap or any protocol that has to say, hey, I'm alive. So if you're on your laptops right now, try this. See what you get. You probably won't have anything if you don't have any external displays. Sometimes your monitor will show up in here too. So when you decode this too, so this userland application you can use to decode. So now start using our imaginations. When we have a hardware implant, but we can also try to get software control with the implant because we're sending data over. We just have to fuzz these binaries. So there's an awesome talk previously by Andy Davis from NCC Group for attacking HDMI, which does exactly this. Because this stuff gets extensive. There's an extension protocol and a defined set of extension blocks, one of which is this 50H, localized string extension, which is exactly what you're thinking right now, a run length encoded string, the size, and then the binary. So if you're starting to fuzz that, there's a couple bytes. Say it's a longer string, say it's a smaller string, you get the idea. But more importantly, there's this FFH, which is an extension defined by the OEM. You can't find the specs from those, they're not published. So you would have to query NVIDIA ATI to see what they're doing, or like, display generator XYZ. So here's Andy's fuzzer. We've gone and implemented that for the BeagleBone to kind of fit with this stack of software and hardware that we're going to release open source. And we have support for fuzzing the stuff the awesome stuff that Andy started, but also trying to discover the formats for those extension blocks. Yeah, more fuzzing. So let's fuzz the stuff that we need to then fuzz more. We need to find it, yeah. You got it. And then to expand on this whole mentality and then like call to arms to start fuzzing these things, there are a lot of other things that support this protocol, this software protocol. So let's start expanding that and going to the set-top boxes and the, whatever the hell it is that supports video and enumerating those extension blocks and throwing them up and hardening them too. Awesome. All right. So I'll throw it back to Josh now.
Okay, so we know our attack surface is VGA, so we're going to use VGA, which is the way for getting I2C keys. So how do we do that with VGA? So like I was talking about before, we need these 4 pins, right? On a VGA adapter, there are pins 5, 9, 12, and 15 corresponding to ground, basically power, I2C, data, and clock. Now some older VGA adapters may not have pin 9 for power, so you just have to watch out for that. Now, the first time I tried this, I was a dum-dum and cut the wrong end of the cable, so I had the fly wire into the VGA adapter, and then I stripped the cable the wrong way. But if you are just looking to kind of power your Arduino or do something cool with an Arduino, you can attach to the VGA adapter, get power, I2C out, run that 2-wire Arduino library, and then you can communicate with an Arduino and do all the cool stuff that you would typically do with Arduino without having to go over the serial debug. So that's kind of like a cool byproduct of using your VGA adapter. So now we know some more information, right? So now we know that the target to video adapter is going to be using DDC, which is also I2C, but now we know that's a more specific version. But we need to fill in the next block, which is the controller. So we need some sort of platform to kind of help us out here. So my platform of choice is the BeagleBone Black. It is if you guys haven't played with the BeagleBone Black, I highly suggest it. It's an awesome board. 1 gigahertz ARM Cortex processor, 512 RAM. A really nice feature is these 2 independent programmable real-time units. So they have like 5 nanosecond guaranteed execution. And about 2 months ago, they released a C compiler for it. So I think there wasn't a lot of attention on these, but if you kind of are into this, right, the C compiler's out, and you can do some pretty cool stuff with these. They're both use like a DMA interface to the Prues. So it also has crypto accelerators, which is kind of an interesting feature for AES. And if you look at my blog, I have some things where I try to get it going for OpenSSL, but I think that's kind of interesting. If you had like a networked attached BeagleBone and you want to offload the SSL processing to the crypto accelerators, that could be interesting. It also has 2 I2C buses, so if you're doing a lot of I2C, you have 2 independent buses. Actually, it has 3, but you can't use 1. So we need one more thing. The other thing we need is, because we're going to improve on the implant with some hardware encryption, so we need some hardware encryption platform, and then we're also going to need a NetMega 320p, which I'll talk about later. So there is a device that will do this. It's called the CryptoCape, which I happen to work in conjunction with SparkFun to make. It has a whole bunch of security ICs. It has elliptical curve authenticators, right? So this will generate ECDSA keys in the chip, where the private key can never be released. So it does 3 NIST curves. Does the same thing for a SHA 256 MAC key. Has an encrypted EEPROM, AES 128 in CCM mode, which is nice. You can either encrypt 32-byte packets to another device, or that key stays in the hardware. Battery backed up real-time clock, so those are all sorts of useful for any kind of security protocol where that battery is dedicated on the cape. The BeagleBone has an RTC, but in order to get the power, you have to actually power it from the test points, because that power rail is connected to the main board, so this one's a dedicated RTC. Has a trusted platform module, which we'll be talking about later, but basically we need to know about the trusted platform module now, or the TPM, is that it does RSA keys for encryption, and those RSA keys stay in the device. Lastly, it has an NetMega 320p with the Arduino 3.3 Pro Mini bootloader. So that's all sorts of useful. the neat thing about the CryptoCape is you can upload sketches from the BeagleBone via the program jumpers, but only if you have the jumpers on. So if you take those jumpers off, you need an ISP programming header to flash the AppMega. And so if you imagine you have some software on the AppMega that you don't want to be manipulated by some software vulnerability, if you take the jumpers off, you kind of have this kind of hardware interlock to make sure that your sketch on the Arduino isn't changed. And then as you can see, it's got all sorts of breakout and all sorts of expansion room to do some fun stuff. So now we know what our controller platform is going to be, and we're going to use the BeagleBone Black and the CryptoCape. That's going to talk over I2C to some sort of video adapter, which we haven't shown yet, and that's going to go over DDC. So now we need this GSM module. So the GSM module that I picked was the Seed Studio GPRS Shield version 2. So this is, you can get this from Seed Studio. It uses the SIM900 chipset. It's in an Arduino form factor, so it's an Arduino Shield. So if you just kind of want a GSM shield just to play with on Arduino, this is a cool thing to get. Quad band support. It has TCP support, so you could do like HTTP get and puts. It's got the SIM card holder on the bottom, right? You can get different service providers. I've tested it with T-Mobile and AT&T. So if you're really paranoid, you can go buy a prepaid, SIM card with cash. And T-Mobile, I thought it had a pretty good deal. $35 unlimited talk and text. So for life, so that was pretty cool. Or as long as GSM was around, I guess. Okay, so now we know some more information, right? So now we know we're going to have the GSM, the GPRS shield, as our GSM reachback. And the way you communicate with the GPRS shield is you use serial UARTs. So we're going to have a serial connection from the BeagleBone. That's going to use the BeagleBone's UART4. There's several UARTs on the BeagleBone. It's going to talk to this GPRS shield. The GPRS shield is going to give us a reachback over GSM. So this is kind of where I got down into a rabbit hole a little bit when trying to make this. How many hardware people do we have there? Okay, so yeah, cool. So basically, the BeagleBone can draw like 460 milliamps, right? So I have a CryptoCape, I've got the GSM shield. All this is being powered from the VGA. So there's no external power. It's being powered from the monitor. The VGA specs basically say, okay, you can have up to an amp, but it wasn't very clear, if that was like widely implemented or if that was like the standard. So I'm looking through the GSM shield, right? If you're talking, it could have this like max 2 amp. Power, so it's starting to freak out, like, oh, this is not going to work. So I ended up making this LiPo power cape, which I ended up not needing because it was, which I'll talk about later. But so the nice thing about the LiPo power cape is you start with a dual cell LiPo, and if you have a switching voltage regulator, you can bring that voltage down. Because otherwise, if you have a single cell LiPo on the BeagleBone, you can come in through the test points that are under the board, but that's only a single cell LiPo, and you're only going to get a limit of 500 milliamps, which is what you'll get on a USB. So to get the 1 amp max, you need to come in with a 5-volt power rail, which coming down from 7.2 with a switching regulator with an inductor on the noise line worked pretty well. So it's a nice cape, right? So the capes are stackable, and you can just stack it and then put a dual cell LiPo, and that'll power this whole device. So the one thing we're missing still is how we're going to connect to the VGA port. So I haven't shown that yet. So this is the Chuck Wagon. So the Chuck Wagon is our code name for this device. And as you can see here, right, it's a little DDC to I2C adapter. It's breadboard friendly, right? So it fits on a 0.1 inch header, which also fits on the CryptoCape and any breadboard that you want to play with. I hate dealing with logic level conversions, so I put the MOSFETs on there so I can have the 3.3 or 5 volt. So if you do want a 3.3 volt system, you have to supply the 3.3 volt. 5 volts will come from the video. Like I was mentioning, not all video adapters will supply 5 volts, so there's a power LED on there. So if you don't see the 5-volt power, you got to provide 5 volts. But very small adapter, and you attach it to the CryptoCape on that expansion header and tie up the I2C lines to the AppMega. The AppMega is on the I2C lines of the BeagleBone. Everything's connected on one bus, and we are set to go. So we're releasing the schematic, the designs, the BOM. These will all be up on our website. So I'm not going to go over this, but it's pretty simple electrically. You basically have the 2 MOSFETs for the logic level conversion, the power indicator. I put a P-channel MOSFET on the bottom. I was worried about people reverse powering the video adapter and blowing up your card, but yeah, so probably not needed, but this is the board layout. And so this technique is not necessarily new. So after I submitted the abstract, this board popped on Hackaday, so I was like, oh, guys. But this is actually kind of a nice board, right? So it's got, this guy put the video adapter, he's got an X-Mega. So the I2C hack is not necessarily, it's kind of been done before, so that's not necessarily novel, but we're not aware of anyone trying to use it as the like an exfiltration capability, besides, of course, the NSA. Okay, so now we have a more complete picture. We have a chuck wagon that's going to provide the DDC to the target, the BeagleBone Black with a crypto cape, serial UARTs out to the GPRS shield, back to remote access. So again, ran into a problem here where the GSM shield is 5 volts because it's made for Arduino, so another logic level conversion. Right, so it's like the bane of my existence here. Then, so when you put everything together with the power cape, which ended up not being needed, right? It kind of looks like this Frankenstein device, right? So I'm trying to use all the different form factors, get it all together, right? So you see the power, the dual cell LiPo. There's 3 stacked capes. One is the power cape. You got the crypto cape, the BeagleBone, the logic level converters, the GPRS shield. But like I said, I didn't ended up needing it. So when I finally actually measured the current using the microcurrent gold, which is an awesome way to measure current. You get nanoamp level resolution. It's very cool. Right, it only peaked out. I saw a peak with everything turned on. If I turned on the GPS at the same time, it just peaked over 500 milliamps. And I wasn't doing any voice, so really ended up needing that power cape. So yeah, Dave Jones, microcurrent gold. Yeah, trusted by hardware implant designers. So I highly recommend it. So if you take out the power pack and you take out the battery, you get a much smaller profile, right? You just have the crypto cape, the BeagleBone, and then the GPRS shield. And then I just put a jumper on there to kind of separate the power. So if I didn't want to have power coming in through the VGA adapter, I can split that off and power it from a different source. With a jumper on, the entire 5-volt rail is connected out the VGA port. So when you stick this in a server, right, or a desktop or something like this, it looks like that. So all the fly wires, because again, I'm trying to use these other adapters. Obviously, if this is all on one board, it could look a lot cleaner, but yeah. So that's what it looks like when it's attached to a target. So the software flow gets a little bit tricky, mainly because of this detail with I2C. And so the thing with I2C is kind of difficult to talk master to master. So your target device is a I2C master. The attacking device is an I2C master. But you need an I2C slave in order to communicate. So this is what the AppMega comes in. So the AppMega is acting as an I2C slave. The way that you target and the attack communicate is they use the AppMega as kind of a mailbox, right? So they write to the slave device, which I just arbitrarily picked address 42. They write, they dump the payload, the other guy picks it up, and right. So there's no notification with I2C, but from the BeagleBone to AppMega side, you can add a GPIO to reduce the polling. So when the GPIO comes on the AppMega, fires off the GPIO, tells the BeagleBone, hey, go pick up your message, and then you can kind of eliminate some polling over I2C. So how do you use this thing, right? So we talked about some potential attack surfaces with EDID fuzzing. So that could be one interesting way to get some malware onto the target. But basically, so the NSA basically said that for their WAGONBED device, they needed a BIOS exploit, right? So similarly, you need to have some sort of malware on the target that is communicating out of I2C. So that's going to communicate, you imagine some sort of kernel module, right, that can communicate over I2C and talk out to the device. And then once that's there, that malware can basically be silent, right? It's just waiting for the device to be attached. It's not making any other external network connections. Basically, no one's looking at I2C, the bus on the PC to see what it's doing, right? So once you connect it, it'll probe for the device, and then you attach your implant, and then you can either exfil or control, whatever you'd like. So if you have the software and you attach this device, what are some of the possibilities? Well, like the NSA implant, right, you can exfil data out to GSM, so the attacking computer has that malware, it sees this implant come in, and it just starts sending data to the AppMega. The AppMega picks it up to the BeagleBone, and it goes out to GSM, and that could go out to voice, text, or it can make some sort of HTTP post. So you don't need the GSM shield, right? So that's the modular capability. So you can just store it on the device. So you imagine some guy coming up to the server, plug in the device, collect the data, plug it out, use it later. You can, because it's bidirectional, I2C is a bidirectional device. If that implant has code for the malware to run, you can give the malware new code, right? So you don't have to go through a network protocol to deliver your malware. You can do it through a hardware implant. And if you can control the implant over GSM, then you can control the target over GSM. And so why is this significant? Well, a lot of people think that they have their network connection monitored, they shut down their USB ports, right? They have no other ins inside the computer, right? most people think of video as being an out, right? But I2C is bidirectional. So you have even if you shut everything down, you always have this I2C bidirectional port that can come into your computer. And it's basically required because in order to do monitor hot detection, you have to read the EEPROM. So on any device, there's going to be an in that's typically not monitored, typically not otherwise looked at, that most people don't think of. And like we talked about before, right, this can work over multiple different monitor adapters. So if you get the Chuckwagon, right, you can put any kind of gender bender or HDMI, DVI. HDMI is actually probably a little better because there is like this hot plug event. But yeah, you can put anything on there and get power from any kind of video adapter and have a bidirectional bus into a target. So there's a couple things that could be done to improve this, right? So obviously it looks a little Frankensteinish, right? So you get everything on one board, you make the implant cape, put it on there, you can get your SIM card, you can get the app Mega, you get your TPM, all in one thing, and that would reduce the size of the device. HDMI footprint versus VGA, HDMI is a much smaller adapter, right? So that'd be kind of nice to shrink that down. You could do this from AVR, so you don't necessarily need to use a BeagleBone. AVR would have the benefit of using a lot less power. I think the BeagleBone's more fun, right? Because then you get Linux and you get Ethernet and you get all this stuff. So, but there's nothing saying you couldn't just do it. You could just do it with the crypto cape if you just applied 3.3 volts to the crypto cape, put your own power supply. And if you think of the crypto cape, it's basically just an Arduino Pro Mini without a power supply. So you could certainly just do it with that. But an interesting one would be to combine Mike Osmond's SalsaFoc with a RF retroreflector and then put an I2C implant on that VGA tap. So if someone looking for a project to do for the Hackaday I/O prize, that'd be pretty cool. And back to me.
Cool. All right, so now you have a pretty cheap NSA implant, all the capabilities from the one that was described in the playbook. How do we make that better? Right, so we've said TPM a couple times. So since we're working on some NSA level shit, we need to take this to the next level. And that is, I don't know, TPMs are kind of corny. I love them. So Josh and I got together and said, well, if you're going to deliver malware through some GSM backdoor over I2C into the video, if someone's on that machine looking at what's running, we sure as hell don't want them reverse engineering our malware or getting that malware off the machine. So if we had the opportunity to drop in an implant, we also have the opportunity to put a TPM on there, generate an endorsement key that stays on that TPM, and exfiltrate the public key for it. So, and it's also kind of cool because now CryptoLocker and CryptoBit are kind of popular. So we wanted to continue that popularity contest of using crypto for badness as just like an example. We don't endorse using crypto for badness. We love trusted computing. There's a lot of good things that come from it. This, if you flip it around, is actually really cool if you want to protect legitimate shit, not just your malware. But, all right, suspend that disbelief. The TPM comes on the crypto cape, which is already hooked up in this Frankenstein awesome looking thing, so you get that for free. So Windows 8 too, going forward, in 4 API commands, I can request a key from the TPM, which means it auto-generates all the stuff that needs to happen on a TPM that we're not really aware of, and it's kind of complicated for you, which includes a password that it manages, and every time you want to request a public key, generate a new one, encrypt or decrypt with that, don't worry, Windows 8's got your back. So what our malware has to look like is just run the 4 APIs, don't worry about anything else. So it's super easy, super low friction to just add a TPM to our hardware implant for free. So we're not creative enough to come up with this ourselves. Actually, in 2011, Usenix Security, there was an awesome paper that described a really complete stack for hiding stuff with the TPM, hiding malicious stuff in the TPM. It's very hard, and it includes things like using Intel's TXT, which is only on Intel only on a subset of Intel chips, as well as a remote attestation method, which is kind of weird science that's never actually been done legitimately before. There are a couple of open source implementations, including Open Attestation, which is a reference model for having remote attestation, but we're missing another key component of that, and I'm not going to keep talking about that. It's hard, right? So this shit is really hard. We're going to relax that a little bit and just say, all right, since we did the hardware implant, we know what TPM's on there, we know what keys on there, we generate generated that a priori so we can attest to the fact that our malware is running on an actual legitimate TPM because we owned that TPM to begin with. Cool. Okay. So here's the kind of stack. Here's the client server CNC model that we kind of relaxed the 2011 Usenix paper to. And that's essentially create a key on the TPM, export that public key, and then every time you want to deliver something to that hardware implant, your CNC is going to encrypt a payload with that public key and then ship it off over GSM to the implant. That's going to run, decrypt it, and execute the payload. So this is kind of the stuff we wrapped most of the hard, like kind of TPM interaction into. And then here's the set of API keys that are required to pull that little red box off. So putting all that together, you now have an encrypted CNC mechanism that'll bootstrap, load, decrypt, and then run your extremely, extremely targeted malware to this specific target. And what do we get out of that? So if we're going to spend the time to go and hardware implant a machine, we want to make sure that no one has the opportunity to go on that, do forensics, and pull stuff off. And if we're sending that data over GSM, if someone were to interrupt that GSM connection, use your imaginations how you would do that. There's actually another talk, part of this playset. And if they were to grab the communication that you're sending to your highly targeted implant, we don't want them to see that whatsoever, right? And we also don't want that going to the wrong implant. So we get a lot of integrity out of putting a TPM onto our hardware implant. Boom. And we're going to give that to you too. So we're going to release that kind of model on GitHub. We're going to take a few things out of it though. We don't just want to release general purpose encrypted malware backdoor channels. So it does have that extract the key. It does have a stub for doing the decryption and then running the process in memory or injecting into another process. But there's a couple things that you have to fix. So if you're willing to take that challenge and you want to know how this stuff works, or if you're just really interested in trusted computing TPMs and you're a black hat dude, go check this out, pull it down, have fun. All right, so first improvement was the TPM. Second improvement is what the hell, there's this bad BIOS shit out there. There's some cool stuff going on. They're exfiltrating over audio, not GSM. Let's do that too, right? Because assuming that our attack model with the TPM was also the GSM connection, someone could interrupt us by just taking down GSM or putting up their own base station, right? So and I'm not saying this is the solution. It's definitely not the solution. There are a lot of caveats that make it wrong, but just to be creative, audio could be a way that you get stuff in and out of your hardware as well. Reference to this, I did some UEFI stuff before, and there were some claims that like there's no audio support in BIOS. I looked at every single OEM manufacturer since 2012. There's audio drivers sitting in the UEFI already, so to exfiltrate from the BIOS over audio is very, very easy. It's already there. You just have to call it. So if you were to go to SparkFun, or if you go to you pick your favorite hardware, open source site, and you buy an audio module to throw onto your hardware implant, what you're going to do is get a nice range of frequencies. So this is pretty much the frequencies of an Apple headset. You get from 20 hertz up to 16, which is kind of us as adults who listen to this loud music all the time, kill our ears to support. So buying one of these really cheap, $3, throw it on your implant, and you'll get this nice wide range of frequencies. And then distance is pretty good too. So I'm kind of trying to eyeball what the max distance through like a $3 audio module would be, running at a frequency that's probably the same as an HVAC system. You could probably get 2/3 to the corner of the room over there. So it's pretty good, pretty reliable. All right, so now we're going to switch into a demo. I think we have 5 minutes left, so it's a good amount of time. While we're doing that demo, we have a couple prizes to give away. We have 2 crypto capes from SparkFun, and we have 3 WAGONBED hardware implants to give away. I know there's not much time left in the con. We threw up 2 challenges, an easy mode and a hard mode. If you have net access right now, if you can go to this website, the challenges are kind of simple. If you solve it, we'll be in the chill out lounge afterwards. First couple of people that come to us with the answer, we'll give these away. If you don't solve it and just like slap us a really good high 5, we might give you one too. All right, let's do a demo.
All right, so I'm going to have you narrate me.
Okay. All right. I can also throw, we'll skip the pictures.
Let me explain the demo real quick. Oh, logistical problems. Yeah, so this demo, what I'm going to do is Teddy's going to show the pictures. Basically, the idea, the whole demo is going to show I want to text a command to the implant that is going to run on the target. So I'm going to text something over GSM, and the target's going to execute it. I'm going to go through this kind of step by step. This obviously can be scripted, but for presentation purposes, I'm going to split up the steps. But you can certainly script this. So we're going to start. I've got 2 computers here. I've got the Beaglebone back, the whole implant plugged into the laptop. The laptop, that device is called Zaphod. So if you see me on a shell, that's called Zaphod. There, I'm a Hitchhiker's Guide fan. AgroJag is the laptop, and so you'll see me switching between the 2. I'm going to show the I2C devices on both buses to show that they're the same. I'm then going to use this ChuckWagon utility to upload a message between the 2, show that that's working, and then switch over to let the implant wait for a GSM text, and I'm going to text it something, see it come back on the target, and then the target's going to execute the command. Hopefully it works.
And the reason we're using this kind of wacky stream from the iPhone over here is because Josh is using his VGA for the implant, right? So we can't be presenting and implanting on his machine at the same time. Without a little bit. Okay. There you go.
All right, so we see all the stuff.
How is that? Is that coming up blurry? Is it good enough? Cool.
All right, so we see both the I2C buses. They're both attached. All right, so that's what that's showing. All right, I am on the implant. It wrote to the app Mega. The app Mega has the word DEF CON in it. I read it back. So if I go back to my host computer, I read, right, it says DEF CON. So they just did that loop, went to the app Mega, posted something, the other guy got it. All right, so now we're going to do the fun one. We're going to text our implant something. Okay, looks like I got cell reception. All right, so this I need some audience participation. I'm going to text
We're here to help.
The echo. Oh, sweet. So I need a number to text it, so that way you know I'm doing this live and all this stuff. So I'll pick a random number. All right, I heard 42, and I'm a Hitchhiker's Guide fan, so that works. All right, so I'm texting my implant echo 42 while they get set up. I hear Jack Daniels makes hardware implants go easier, so.
Improves your demo success.
Yeah. All right. Yeah. Okay. Shot before or after we see the text works? What do you think? Okay, we'll wait after. All right, well, hopefully.
We want to see it.
Okay.
See me texting to the phone?
Oh, yeah. So I texted it over. I'm paranoid, I texted it twice just to get there, but you see it.
Yeah, it's good.
All right, cool.
Got the idea.
All right, so if I read back from the ChuckWagon device, echo 42. So we got it, right? So then if you imagine this is all scripted, right? So I'm just doing this for presentations. Damn. What?
Should have done the shot before.
I know. Oh, because I'm on the wrong device. There we go. I want to do, 1 second. Oh, damn it. Well, we'll just read it from here. Basically, if you just execute what's in, yeah, so both devices have it, and for whatever reason, I'm not seeing in the history of the bash, but you can imagine, right? You bash that, execute it, take that command, you script it, pipe it to bash, right, and then it's going to execute. So
We all know why it didn't work.
Right, yeah,
It didn't
okay, all
do
right.
the shot.
All right, there we go.
All right, I do not know what's going on in here, but it looks awesome. So fuck it, let's do it live.
All right.
New speakers, love.
Cyber.
I'm sorry. Track one, the entire conference has been a bit lame on their love. So I want to really hear it for these guys. Come on! That's what I'm talking about.
Rock and roll.
All right. And do we have any time for questions? We got 10 minutes for questions. Sweet. So while people are thinking about questions, can we go back to the slides?
Yes.
I'm going to put some shameless self-promotion for a book that I'm writing, which has a nice pre-order discount. So if you like what you see there and you want to check out this book, I do some cool stuff with the BeagleBone and Crypto Cape. And if you pre-order from Pact, you'll get a sweet discount. All right, is there any questions? Yeah, go ahead.
Can you do pass-through on the video so you can still run a second slide while you're on the video?
Yeah, so I've tried to do like with a Y-splitter. So that was the original idea. I wanted to have a Y-splitter, then hook it up. The Y-splitter, I'm not sure if it's just the Y-splitter I used, but it dropped too much voltage, so I wasn't getting enough power. And so I'm not sure if that's just like the cheap Y-splitter I got, or if that's an artifact of just trying to do that at the same time. But yeah, that'd be pretty cool, but I did try it. It was a fail. Any other questions?
That was a great question.
Yeah, thanks. Not seeing any? No questions? Okay, cool. Well, the code is up on GitHub for that whole demo, so if you go there, you'll be able to see it. And thanks so much for coming out.